We've already mentioned the many types of meteorological conditions that can affect aviation operations. For the remaining portion of this program, though, we're going to limit our focus on one type, icing. Icing can have a profound effect on both the in-flight and ground operations of aircraft. Let us visit two NASA research centers that are involved in various icing research studies. We'll start our icing travels by visiting NASA Lewis Research Center in Cleveland, Ohio, and its icing research tunnel. Now, this facility is the world's largest refrigerated wind tunnel. So bundle up. Let's go visit this giant cooler and have a closer look at icing effects on aircraft and the icing research being conducted. Listen to learn how one measures the effects of ice on aircraft performance.
Thanks, Shelley. My name is Dr. Judy Foss Van Zanti, and I'm standing in the test section of the icing research tunnel. Right now it's nice and warm in here, but later on it's going to get really cold. All right, what this tunnel was built for was to simulate down here on the ground what it's like for an airplane to fly through an icing cloud up there. We do this by creating a cloud that mimics what you see up there. As one of the research engineers, I asked the operators to select 5 parameters. One is the airspeed coming past the model. One is the temperature, how cold it is, always below freezing. 2 parameters are about the cloud density, how much water I have in the cloud, and also how big each drop size is. The final parameter I select is the time that I'll be flying through that cloud. I select the cloud conditions, I select the model, I either select an engine, which provides the airplane forward thrust, or I select a wing, which provides the plane lift, and I want to see one of 3 things. One is, what kind of ice do I grow on my model? What does it look like for the given cloud condition? Another thing I might want to look at is how to keep ice from growing on that, an ice protection system. And a third thing I might want to look at is to see how well I can predict what the ice shape is going to look like using a mathematical model and a computer. All these 3 functions are done in the tunnel. I use this tunnel along with Tom Rutvaski for the tailplane icing program. What we did there was to see how ice contamination affects the operation of the tailplane. Let's take a look at what the tailplane is and how it affects the aircraft operation. What we have here is an animation of an airplane in flight. The forces acting on this airplane are the weight, which acts through the center of gravity. The upward lift is provided by the wing, and the tailplane on the right side of the screen provides a downward lift. In equilibrium flight, we've got the following force and moment balances to consider. We've got the weight, which acts through the center of gravity, which is also the aircraft's pivot point. That's always forward of the wing center of lift. Those 2 forces acting together create a nose-down pitching moment. The tail comes in to provide a downward lift. As you can see, that's a simple geometry problem. The plane acts an awful lot like a seesaw. The tailplane icing project that Tom and I worked on investigated the question, what happens if you move that wing center of lift further back? How does that affect the tailplane if you've got an ice shape on it? We at NASA Lewis Research Center took this information and gave it to the pilots so they can make better and safer operating decisions. Back to you, Shelley.